differentiating inverse trig functions. I'm going to start with this, which Rain has seen before. Is that too hard to read?
It's just the right side.
Okay.
Yeah, got it. It's fine.
dy dx is 1 over dx dy. Do you believe me?
Mm-hmm.
Oh, that was easy. You're okay with that? You don't need me to give you an example of why that happens? Julia's thinking.
No, it's fine.
You believe that? Okay. If you believe that, then I can get you there. So, this is a little...
Why wouldn't I believe that?
Because these are really limits as this approaches 0. So it's a little bit complicated. I'm not going to show you first principles. I would just draw some lines for you and see how it worked for a straight line. I'm swapping x and y, so the gradient of the swapped one is going to be 1 over the one I had. Okay, if you believe that, then let y equal arcsine x. Well, if y is arcsine x, then I know two things. X is sine y, and there's a restriction on what I can get. Sine negative pi on 2 less or equal to y less or equal to pi on 2. Because arcsine of x is in here. So I know I'm in that area. Okay. Then, which way am I doing this? dx dy is cos y. Right? Differentiate this. With respect to y, it's a little unusual, but that's what we're doing. So then dy dx must be 1 over cos y. Yes, okay. But sine squared, am I doing x or y? Sine squared y plus cos squared y is 1. We know that already. So, cos y is plus or minus the square root of 1 minus sine squared of y. Yes? I also know that it's going to be positive because cos y is positive in this domain.
I did this yesterday. Not yesterday, the day before that.
You did something like this, yes. Maybe that's right. You did a little bit of this in one of those questions.
You just did it a lot longer.
Okay. This is here and here. Oh, actually, even let's draw it here. So we're talking about here and here.
Yeah.
Cos is positive on that side. So actually, I don't even need that. Okay. Cos y is this. How does that help me? Oh, dy dx, therefore, dy dx, which is the derivative of arcsine, is 1 over the square root of 1 minus x squared. Again, you don't have to be able to go through all this. It's not required by the syllabus, it just says use the derivative. But that's why this weird expression is the derivative of arcsine of x. Like the textbook, I think it's worthwhile you going through that once or twice. So I'm not going to show you how we got cos to minus 1 and tan to minus 1 derivatives, because they do turn up as questions later in that exercise, in the next exercise you're about to do. What you have to be able to do is apply those rules from the formula sheet to calculate those derivatives. Let's try some. And that's supposed to be better. Okay. Arccos 3x plus 2. Both have unions. Is that readable back there? You can read that?
Yeah, that's good.
So I should try and make it a bit thicker.
It's okay.
That better?
That's fine.
Okay. What's dy dx? Well, arccos we just learnt. X on A. Not quite sure how to do that. Hey, this is not x on A, is it? But I can just use the chain rule, right? So this is my x in here. So I'm going to go negative 1 over the square root of... Oh, did they really do that? They did. Do you want me to show you a full detailed chain rule, or just do it as usual?
Do it as usual.
Okay. So the square root of 1 minus 3x plus 2 squared that's this multiplied by derivative of the inside. Do you want me to do the full writing out with a U?
Just say it, you don't need to write it out.
Well, it would be leg. I'll write it anyway.
You don't need to.
I will.
Okay.
It's good practice. Let u equal 3x plus 2. So du dx is 3. So y is arccos u. dy dx is dy du du dx, which is arccos negative 1 over the square root of 1 minus u squared. Du dx is 3.
Where are you getting 1 minus 2? A is 1.
A is 1. X over what? U over what? U over 1.
Yeah.
Which is what I had before, negative 3 over the square root of 1 minus 3x plus 2 squared. Yeah, book. I wouldn't go any further than that. If you have to do something else with this, I might consider expanding those brackets and simplifying what's underneath. But just to find the derivative, that's good enough. you go. Apply the rule. You got it, Julia? No.